Hello and welcome to this PIR Live Event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Remember, you can ask questions anytime during the webinar or the talk at the beginning by clicking chat near the top left of your screen and typing out your question. Make sure you select to send that question to everyone so that all of our participants today can see what other students are asking too. Give us the name of the student asking, your school, your teacher, your city, tell us where you're joining from, and we would be happy to give you a shout out when we ask that question on your behalf. So I'm pleased to introduce you to Dr. Lyle Whyte. He is a professor in the Department of Natural Resource Sciences at McGill University, and he's also a member of the European Space Agency's ExoMars 2020 Landing Site Selection Working Group, among other things. Thank you so much for joining us today, Dr. Whyte. I'll let you take it away.
Thank you very much, Stacey, and a big hello from Montreal to everyone across Canada. I see many people from Calgary that are present. I actually was born at the Foothills Hospital in Calgary way back when. I won't say how far way back when. I'm just going to get my presentation on here, and we'll start the presentation today. Let's see if I can get this to work. Share screen. Here we go. I'm going to blow it up, and we will be in business, hopefully. Great. So as you can see, the title of the presentation is something called Astrobiology. And astrobiology is really looking for life beyond Earth. So this talk that I'm going to talk about is astrobiology, the search for little green microbes on Mars and other really, really cold worlds. And those cold worlds are shown on that slide. I'm an environmental microbiologist. I specialize in polar microbiology. Basically, if I go to the next slide, it kind of sums it up. I specialize in microbes that exist and grow in the coldest places on this planet. We call these microorganisms are called prokaryotes. The questions that we're trying to answer are indicated on that slide. What are the cold temperature limits of bacterial life? Are frozen environments, cryo environments, biologically active in situ? Because we don't really know that. And then there's this astrobiology relevance in terms of looking for life on places like Mars and these two moons called Europa and Enceladus, which are all basically just frozen ice balls. The picture that you're seeing in the background is a wonderful place. It's in the Canadian High Arctic of Canada on a place called Axel Heiberg Island. And your homework tonight is to find out where that is, but I'll show you a map anyways. We have a McGill Arctic Research Station, and this is the map that kind of shows you what the places that we do our research. So Montreal is right down on the bottom there. And you can see on the very top a place called Expedition Fjord, and there's also a place called Eureka, which is on Ellesmere Island, and Expedition Fjord is on the island just adjacent to that called Axel Heiberg, and the McGill Arctic Research Station is located there, and that's where we do most of our research. So let's get back to Mars and looking for little green bugs on Mars. It's our favorite astrobiology target, mostly because it kind of looks like Earth and it's also pretty close by. And the other reason is about 4 billion years ago, from what we know, what we think, the idea is that Mars was much warmer and therefore wetter, that there was oceans and lakes and rivers and those sort of things. And of course, water is one of the key ingredients for life as we know it on our planet. And then about 3.5 billion years ago, something happened. No one knows really for sure. And Mars turned into its present situation where it's quite cold, very dry, and much more extreme than it was 4 billion years ago. So this is the kind of slide I would show at a conference, and it says, you know, the Mars surface is not habitable in terms of any type of life on Earth as we know it. It's too cold, way too cold, well, maybe not too cold, very dry. And these last 2 points are important, is that there's way too much radiation and there's some very nasty chemicals in terms of perchlorates that exist in the upper crust of the soils that you see. And that picture is coming from Curiosity Rover in the Gale crater, which is still driving around Mars today as we speak. So on the surface, we do not know of any microbes on this planet that could exist on the surface of Mars today. But I'm going to take you to ExoMars 2020 now. So ExoMars 2020 is a mission that will take off in 2020. It's led by the European Space Agency to send another rover to Mars. And this is a picture, actually it's a very sexy picture of what that rover looks like. It's not nearly as dramatic. The most important part about it, though, is it has a drill. And I'm going to see if I can, I don't know if you can see my little mouse moving around, but the drill that it has will allow it to sample below the surface, hopefully, about 1 to 2 meters below the surface into the subsurface. And for the first time on Mars, we will actually, hopefully, retrieve samples from the subsurface where all that radiation and bad soil chemistry will potentially be avoided. And then there's instruments on board, the Rover, life detection instruments that are going to look for evidence of past microbial life and maybe what we call extant microbial life, which is basically life today, looking for so-called biosignatures, things that indicate the presence of very dead old microbes or current microbes, if you will. So I was chosen to be part, I'm the only Canadian actually, that's part of the something called the ExoMars Landing Site Selection Working Group, which basically is a group of about 20 scientists and then about 20 engineers. The scientists want to tell the ExoMars people where to land the rover in terms of answering the science questions of trying to detect life on Mars. And the engineers, their responsibility is to land the rover safely as best as possible, because it's about a $3 billion mission. And of course, if you don't land safely and you crash and burn, that's a big problem. So there's a big fight between the scientists and the engineers. The engineers want to go to the flattest place possible, and the scientists want to go to the place where we might have the best chance of finding life. So we look a lot of these things called ellipses, what you see here. And if you look in the middle of this ellipse, you can see what looks like a riverbed or a dry riverbed. And this is what makes this particular site so interesting. And it's one of the 3 finalists for ExoMars to land on, because there are around this riverbed, which indicates water or ancient water anyways, floodplains and so on and so forth, which contain sediments that are basically the target sediments. And this picture is a little bit complicated, but I just want you to focus on this part up here, where it shows you ExoMars and that drill. And as you get deeper and deeper and deeper into the subsurface, as indicated on the x-axis, the longevity or the survival rate of organic molecules like amino acids, which indicate life, increases exponentially or at a very significant rate, so that when you get down to 1 to 2 meters, you have a much better chance of detecting these so-called organic biosignature compounds than you would if you were just looking at the surface, which is indicated here. So that's sort of the idea of ExoMars 2020. You may ask yourself, is there water on the surface of Mars today? And I would just describe that a little bit more and say, is there cold, salty water on the surface of Mars today? And there is evidence of this now. These things are called reoccurring slope linea. And if I go, you see these dark patches on the side of this hill here, indicate that water has come out the side of this hill and streamed down. And there is an orbiter that is orbiting Mars as we speak, it's part of Curiosity actually, that has looked at the chemistry of those slope regions. And we know with a certain degree of confidence now that that is cold, salty water that has recently come to the surface of Mars, which makes that a very interesting target for microbial life. And you may ask yourself, why? And I'm going to show you some whys, why that might be important. So I'm going back to the actual Heiberg Island now, and I'm taking you to a place called Lost Hammer Spring, which is a sub-zero hypersaline methane seep in the Canadian high Arctic. So the actual spring is right here, and this is on a beautiful July day about 5-6 years ago. And what you see around this spring, you can see some of the channels coming out, is really basically salt deposits. So the water in this spring is very unique. This is in an area, a very extreme cold area. Average temperature is -15 degrees C. Winter temperatures down to about -50 degrees C. The permafrost where the water is going through, coming through the spring, is about -16 degrees C. And the permafrost in this area is 600 meters in depth. So a very cold, cold place. If you go inside that little area here and jump in, and I have a picture here of 2 of my former students that have done this, there is the spring in this area here. Oops, sorry, let's go back. And they contain sediments and water. The water is very salty. It's about 25% salt, almost 3 times that, or 10 times that of seawater, and it's always at a temperature of -5 degrees C. And then you see all these wonderful other pieces of data that indicate there, these are things for microbes to eat and breathe, essentially. So this is a bit of a eureka area in the terms of looking for life in really cold places. And what do we find there? Well, on the bottom of the slide, we know from our research, we published this, that it contains an active microbial ecosystem. And you're going to have to come to McGill and take microbiology for me to understand what the rest of that stuff means, but I'll just try to make it very simple, is that we know that there are very salt-loving organisms present that can grow at -5 degrees C. And what do they eat and breathe? Well, there's things called archaea, or ANME1 archaea, which essentially eat methane instead of, breakfast like you did. And instead of breathing oxygen, they breathe sulfate at -5 degrees C and 25% salt. So that's the kind of organism we might think we might be on Mars. Okay, moving along. I'm going to take you now to Jupiter. And this is a moon of Jupiter, which you may have heard of. It's called Europa. And it's basically a giant frozen ice ball. It's covered by we think about 30 to 50 kilometers of ice. It's got all kinds of cracks and fissures that you can see there. And underneath that ice is an ocean that covers the entire moon. It's about 200 kilometers deep. So this has become a very interesting place. It's been like this for about 3 billion years, the planetary scientists that tell us. And it's the target of future missions in the 2020s, which you're going to be watching on TV and so on and so forth. It's called the Ocean Worlds missions. And here is a cartoon of what that might look like. So you can see Jupiter in the background in the right-hand corner. Those cracks and fissures are actually kind of interesting because they're places where water is coming to the surface of that moon, which make them really interesting places to sample. And you can see some interesting little tiny happy faces on the bottom there, which are apparently supposed to indicate something living like microbes. And we think that this ocean that you see in the bottom, again, is a salty, very cold ocean, which again makes it the polar research that we do relevant to what we're looking for. So now I'm going to take you farther out into the Saturn system to a place called Enceladus. Enceladus, which is, again, just by looking at this thing, a very tiny moon, actually. It's one of the brightest spots in our solar system, but it's quite tiny. Covered in ice, like Europa. And it has one very interesting feature that we've discovered in the last 10, 15 years. And the picture on the right shows that. There are geysers on Europa that are spewing out into space cold, salty water. And the Cassini mission, led by the ESA by the example, has flown through these plumes that you see here and analyzed some of the molecules that are present in that plume. And what I can tell you is this, is that first of all, it's water, it's salty water, and it contains a whole bunch of interesting compounds that you see here, including organic molecules, carbon dioxide, ammonium, methane, and so on and so forth. Now, if I were to take that cocktail of molecules and put it, put it in my beaker in a lab and try to grow microorganisms from soil or someplace, I would be able to do that on Earth. So what we're really doing is showing that is definitely the water that's coming out of the subsurface of Enceladus is the kind of environment where we can certainly envision microbes could exist. Whether they do or don't is something that in your lifetimes you will probably find out as we send these missions to answer those questions in the 2020s and the 2030s and beyond that. So these will be exciting times as part of your lives. I'm going to finish off very quickly talking about something called wait a minute, I'll have to show you this first. So, I've just shown you 3 cold, icy worlds, Mars, Europa, and Enceladus. What kind of microbe might live there? Well, here's one of them. It's called Plano caucus halocryophilus. It's called caucus because it's round, and you can see these 3 blobs there, 3 or 4 blobs. Those are the actual cells that look pretty weird. This organism comes from Ellesmere Island permafrost, which we discovered and reported on over the last 5 years. It's the cold temperate champion of the microbial world in that it can grow at least down to -15 degrees, reproduce, in about 19 or 18% salt. And we know that it can be metabolically active at least down to -25 degrees C. And what I mean by that is, it's breathing like you are right now and doing things and functioning, so on and so forth. So I'm going to finish this off then by talking about exoplanets, which you've probably heard about. Very popular, sexy topic in the scientific news, popular news these days. And exoplanets are a big deal. In 1995, about 1995, we discovered the first exoplanet, or the astronomers did. And since then, thousands of these things have been discovered. And our current concept of our own galaxy now is that just about every star has planets. And about a quarter of those stars probably have planets that are probably Earth-sized in the so-called habitable zone, or the Goldilocks zone. So what does that mean? Well, here's an example. This one's called Kepler 22b, which would be within the orbits, or similar orbits around a similar star than our Earth is. And the green area that you see is the so-called habitable zone, which really means, in terms of habitability, is that water could exist on the surface of that particular exoplanet, which means that it could be potentially habitable as far as life as we know it on Earth. Anyways, so in the future, we will be launching bigger and better telescopes. And one of the things that we're going to try to do, I'm looking at this slide here, so this one might be a little bit more complex, but this is an exoplanet very close to its star, but you can see the haze of its atmosphere surrounding that planet. And we now have the instruments that are going to be launched in the next 5-10 years that are going to look at the haze and determine what the chemical structure is of that haze as much as we can. And if we find, for example, things like ozone or oxygen, or maybe we'll get really lucky and see a spectrum of chlorophyll in such a type of atmosphere, which would indicate to us that these are the type of places that potentially could be planets that have life. So that is where I'm going to stop. I know I talk too fast, but I try to get a lot of information in there, but I'm thrilled to give this presentation. I have 4 kids myself, 16 years old, 15, 12, and 9. So I hope you learned something today, and I'd be thrilled to answer any questions that you have. Thank you very much.
Well, thank you so much for showing us so many visual representations while you were speaking as well. I think that's very helpful for our viewers to understand what it is that we're telling them about. So if you want to go ahead and click the stop share button that's red at the top of your screen, then we'll be able to see your face a little larger. There we go. Our questions. Now we have had lots of questions coming in, so we'll get to as many as we can. The first question is from Mrs. Martin's grade 4 class at Wainwright Elementary School in Irma, Alberta. They would like to know, what is the temperature range on Mars? We talked about it being really cold. We didn't really quantify that.
Yeah. Well, the average temperature, if you can come up with a global average temperature, is about -60, -70 degrees C. Having said that, the temperature range can be above 0. We think maybe 10 degrees C on the equator and low elevation, low-lying areas. During the night, it gets down to about -120, -130, something like that. So Gale Crater, I think the average temperature is about -50, -40, in that type of range.
And our next question comes from Emma in Ms. Sampson's class. They were grade 5-6s at Summit Heights Public School in Toronto. They want to know, do you have any sense of how likely it will be to find evidence of life on Mars or any of the other places that you were discussing?
That's a great question, Summit High School. You know, I'm a scientist, and as a scientist, we have hypotheses, and then we have research objectives or questions, and you just asked a very interesting research question. What is the likelihood? We don't know. When we go there, we are going to, over the next 50 years, part of your life, there'll be more and more of these missions going to Mars. There'll certainly be more missions going to Europa and Enceladus, trying to answer that question. If I were a betting person, the best chance, I'd be putting my money on Europa or Enceladus, just because I know there is liquid water on the surface, or not on the surface, but there's liquid water environments there. On Mars, I'm not so sure. Definitely in the way distant past, about 3.5 billion years ago, the planet was more habitable. Whether it ever had life or not, I just don't know. And that's why we send these probes.
Right. And as you said, we may find out in our lifetimes here. So if you find life on Mars, the Summit Heights Public School class would also like to know, what would you do with it? Where do we go from there?
Okay, that's another great question. This is like, I would tell this to my mother. So why would we go to Mars to look for microbes? Okay, that's basically what you're saying. It will be one of the pivotal discoveries of science in this, and certainly in this century, probably for a very long time, that we would discover that we are not alone, that if we can find life on Mars, for example, it probably means that the life is spread out through the galaxy in terms of other planets and other moons, especially if that life turns out to be quite a bit different from the type of life we find on Earth. And we will have the tools to determine that, because we can use our DNA sequencing methodologies, for example, to identify or characterize the microbes that might be on Mars, for example. You know, so it would be, are there two origins of life? And I can get really philosophical here about what that means to me, but I won't at this particular stage in terms, you know, it tells us something about, are we really alone? If we don't find life on Mars, that's equally kind of interesting to me. You know, and I kind of wrap it up in philosophy, and this again is all very personal. My perspective, you know, is there a God or is there not a God? And for some reason, I tie this into looking for microbes on Mars. But I think that's for another day, another discussion.
I hear you, and I'm sure you're not the only one with those types of questions, for sure. So moving along to another class now who's joining us, we've got two similar questions here, so I'm going to throw two at you.
Okay.
Ms. Payne's class wants to know, how do you know what Mars was like 4 billion years ago? And Ms. Davies' class in Calgary wants to know what caused the change that you discussed from what it used to be to what Mars is now.
Okay, so just keeping in mind I'm the microbiologist and not the planetary scientist. From what I know about this topic, we do know that Mars was definitely wetter a very long time ago. We can see these evidences of dried up rivers and things like that, and lakes, and you know, Mars Curiosity rover now has landed basically on a lake in the middle of a crater. It's proven that. We do know the age of it because we can count the craters that are around these structures, and by counting craters, we can get an idea of how long back those types of geomorphological features such as rivers and lakes and oceans and those sort of things were formed, and how long they lasted. So the planetary scientists would tell you, based on those type of things, crater counts, that this area is about 4 billion years old or 3.5 billion years old. The Arm Dorsum site that I just showed you, based on crater counts, is about 3.7, 3.8 billion years old. That's when that river was flowing. And the other part about it, if there was water flowing on the surface, that means it was definitely warmer. What happened 3.5 billion years ago? I think you're going to have to invite a Mars planetary scientist to one of these webinar type presentations, and maybe that person will be able to answer that question better than I, because I don't know.
Well, thank you for trying. Yeah. Good to know. Not everyone is an expert in everything. We've got our next question coming from Burford, Ontario. Mr. McCleary's class would like to know, how can you retrieve soil samples from a place so far away like Mars?
Yeah, I mean, that's a great question as well. I look at these missions, you know, when you think about this, we are sending a robotic spacecraft that launches from Earth, flies about 60 million kilometers to another world, to another planet, and then we call it the white knuckle time, and where the thing has to land. And right now, our success, mankind's success of landing things on Mars is about 40 or 50% of the time. And then if the thing lands and it still works, which is always a problem, you know, and everything's working, so how do we get samples? Then we have to get these samples through the sampling instrumentation. It's all robotic. It's all taking commands from Earth, essentially, and delayed 20-minute time. So technically, logistically, this is a very complex and difficult thing that we're trying to do. The idea of drilling into the subsurface, which I've drilled into the subsurface of Axel Heiberg Island, again, very difficult to do robotically. You can encounter all kinds of problems, and to retrieve a sample from that robotic drill, bring it up to the surface, stick it into the spacecraft, into the instrumentation on board the spacecraft, technically hugely challenging from many different perspectives. So you need great, bright people with expertise as engineers, mathematicians, microbiologists, guys that build things, people that build robots, so on and so forth, astrophysicists, and people that make rockets and figure out how they can land, you know, send a rocket and get it to Mars in the right place at the right time and hit that ellipse that I just showed you. that make sense?
It sounds a little bit intricate.
It is, you know, it's like I kind of view it as sort of the, you know, one of the pinnacles of humanity that we've managed to do those sort of things of landing, for example, Mars Curiosity rover on the surface of Mars. That thing is about the size of a small car. We did it, and everything worked on it. It's been there for like 3 or 4 years, still driving around on the surface of Mars, and mostly, for the most part, still working.
And we've had a few questions come in from across the country. Students would like to know, how long can you expect one of these rovers to be in action at its destination?
Yeah, well, the Mars Curiosity rover was designed, I think, to last for 2 years. That was sort of the minimum design window. If it landed safely and everything worked, it has a nuclear power source, I believe, and which allows it basically to run forever. And it's basically a question, when are the mechanical parts going to break down? Some of those parts have actually started to break down. But it's been there for 3 or 4 years. If everything works well and the engineering was done as good as they think it has been, they figure it could potentially putt around for about 10 years. Okay.
Wow.
There's 2 rovers on Mars, one that's crashed and died, and the other one, which landed about 10 years ago, the Spirit or Opportunity rovers, one of them is still working. So, you know, it's basically how well did we build the rover, and do we still have power to drive to power it?
Right. So to shift gears a little bit here, we've also had many different classes asking about plants rather than the robotics. So for example, Zoe from Brayside School would like to know if there's any evidence that plants used to grow on Mars, or could, lots of other students wanted to know, could we ever grow plants on Mars in the future?
Yeah. I think, you know, obviously some of these people have seen The Martian. Great movie, by the way. Has there ever been plants on Mars? The answer to that is we don't know. I can tell you that based on the environment that we know, that we think existed on Mars 3.54 billion years ago, it was still what we call an anaerobic world. There was no oxygen or very little oxygen. So just because of that, and from what we understand of life on Earth, we think that the best possibility of life on that planet was microbial. And by the way, some microbes are plants, in a sense. They can do photosynthesis and use chlorophyll. Cyanobacteria, for example, basically are the precursors of plants, blue-green algae. Can we grow plants on present-day Mars? From what I know about this, and I'm not a Mars plant botanist, yes, we can. There are soils on Mars that look like there could be adaptable to growing things. You probably have to add water and fertilizer, just like you have to do in the West when you have a drought, so on and so forth. Yeah, but it certainly could be. It certainly could happen.
Excellent. And I'm going to try and squeeze in 1 or 2 more questions here before we sign off. Lewis students are wondering if there's any potential for fossil life. So maybe if we don't find life currently, can we establish whether there has been life in the past?
Yeah, I mean, that's basically what Curiosity rover is looking for, as well as ExoMars 2020. When I say past life, I mean fossilized life. You know, can we find fossilized microbes or evidence thereof in the rocks and soils of Mars? Yeah, we're looking for the molecules that could exist. It's possible that we might be able to see like a microbial fossil. We have microbes that grow within rocks on Earth. We study those. They are called endoliths, basically, and you can see them with your naked eye. And we have other things called stromatolites on Earth that are 3.5 billion years old that contain fossils of microbes. So yeah.
Wow. Okay, so I think 2 more questions here. Mr. Cull's grade 6 class at Simmons Valley School in Calgary would like to know, could microbes be used to terraform Mars?
In science fiction, yes. I mean, yes, you could think of, if there are no microbes on Mars right now, and this is the big question, we have something called planetary protection, where we want to make sure that we don't bring any Martian microbes back to Earth that could cause undue harm to humanity or to our ecosystems. And at the same time, if there are microbial ecosystems on Mars today that exist, we do not want to contaminate them with foreign invasive species of Earth microbes? So those are, good questions. But let's say there's not, and we don't discover anything. Can we use microbes to potentially terraform Mars to make it more hospitable? There are people who are looking at that. I don't think it's going to happen in our lifetimes, but the potential is certainly there to use some Earth microbe like the one I showed you that can live in an anaerobic world like that. And if you add just a few things, that they would start growing, maybe increase the concentration of the atmosphere so it starts retaining water better. And then, things can happen. You might be able to heat up the surface and then get liquid water on the planet again.
There are just so many things to think about with all of this, it seems. Very interdisciplinary. I understand now why there are teams for everything with different expertise. So I don't want to keep everyone much later than we said. We're a little bit over our time already. Maybe I'd like to see what you have to say. If you have anything you'd like the students to know, should they really be interested in these topics, maybe advice for them or just research in general?
Well, I mean, as a researcher, a scientist, I think it's a great career. I love my job. I can tell you that in the next 30, 40, 50 years, this is going to be the golden age of planetary exploration because of all the great advances that we have made in terms of building better rockets, and there'll be private companies sending rockets to places and all kinds of probes going on. So it's going to be a tremendously exciting time. The places that I just showed you, we will be answering some of the questions of whether or not we can find microbial life on places like Europa and Enceladus within the lifetimes of many of the people who are listening this morning. So if you have an interest in science, if you have an interest in planetary science and these sort of questions, go for it. I had no idea 10 years ago, even 10 years ago, that I would be part of a committee that was going to decide where a spacecraft was going to land on Mars. Okay, so just go for it. Even Canadians can do this.
Right. Well, thank you so much. That's all the time we have. Thank you to everyone who joined us today, and thank you especially to Dr. Whyte for answering our questions and sharing his expertise in astrobiology.
It was my pleasure. Thank you very much.
So next week on PIR Live Event, we're talking about fisheries, fish health, and climate change. More information on this and other upcoming webinars can be found at pirweb.org. Thanks again for joining, everyone. We'll see you next time. Bye-bye.
Bye.